You think you understand water. You drink it, you swim in it, you wash your hands with it. Water is wet. Water flows. Water takes the shape of whatever container you put it in. It's a liquid. Liquids don't hold things up. Things sink in liquids or they float depending on whether they're lighter or heavier than the water they displace. Simple. Obvious. You learned this when you were 5 years old. Now explain the water strider. Go outside, find a pond, look at the surface. There's an insect standing on the water. Not floating, standing. Its legs aren't submerged. They're resting on top of the water like the water is a sheet of glass. The insect walks. It runs. It jumps. And the water doesn't break. The water doesn't let it through. You've seen this 1,000 times. You've probably never stopped to think about how absolutely impossible it should be. Water is a liquid. Liquids don't have surfaces you can stand on. Liquids flow around things. If you put your finger on water, your finger goes in. If you drop a pebble, it sinks. If you set a paperclip on water carefully, flat side down, it floats. But if you push it, it goes right through. So what's happening? What's holding that insect up? Most people have a word ready. Surface tension. They say it with confidence, like the word explains something. Surface tension. The water has tension at the surface. That's why the insect can walk on it. Stop. That's not an explanation. That's a label. You've named the phenomenon. You haven't explained anything. It's like asking why fire is hot and being told it's because of thermal energy. That doesn't answer the question. That just replaces one mystery with another word for the same mystery. Why does water have surface tension? What is surface tension? What's actually happening at the surface of the water that creates this invisible skin? Let's start where we have to start. Let's start with atoms. Water is made of molecules. Each molecule is 2 hydrogen atoms bonded to 1 oxygen atom, H2O. You know this. But do you know what that actually means? Do you know what a water molecule actually is? It's not a little sphere, it's not a bead, it's a configuration of charged particles. The oxygen atom has 8 protons in its nucleus, positively charged. The hydrogen atoms each have 1 proton. Around these nuclei, electrons swarm in probability clouds, negatively charged. The molecule as a whole is electrically neutral, but the charges are not evenly distributed. The oxygen atom pulls on the electrons more strongly than the hydrogen atoms do. So the electrons spend more time near the oxygen. This makes the oxygen side of the molecule slightly negative. It makes the hydrogen side slightly positive. The molecule has a positive end and a negative end. It's what we call a polar molecule. Now put 2 water molecules near each other. What happens? The positive end of one molecule attracts the negative end of another. They pull on each other, not with enormous force, but with enough force to matter. This attraction between water molecules is called a hydrogen bond. It's not a true chemical bond. It's weaker. But it's there, and it's constantly acting between every water molecule and its neighbors. In a glass of water, every molecule is surrounded by other molecules on all sides, above it, below it, left, right, front, back, molecules everywhere. And each of these neighbors is pulling on it. The molecule in the middle feels forces from all directions. These forces roughly cancel out. It's being pulled up and pulled down, pulled left and pulled right all at once. The net effect is that it can move freely. It jiggles, it bounces, it wanders through the liquid. That's what makes water liquid. The molecules are attracted to each other strongly enough to stick together, but not so strongly that they lock in place. They can slide past each other, they can flow. Now think about a molecule at the surface. A molecule at the very top of the water, right at the boundary between water and air. What's different about its situation? Below it, there are other water molecules. To its sides, there are other water molecules. But above it, nothing, air. And air molecules are not water molecules. They don't attract water molecules nearly as strongly. For all practical purposes, the molecule at the surface has neighbors below and beside it, but almost no neighbors above. This creates an asymmetry. The molecule at the surface is being pulled inward and sideways by all its water molecule neighbors. But there's nothing above it pulling it up. The forces don't cancel out. There's a net inward pull. Every molecule at the surface feels this. They're all being pulled down into the bulk of the liquid. But they can't all go down. There's only so much room. So they pack together as tightly as they can at the surface, minimizing the surface area, creating a kind of tension. That's surface tension. It's not some special property of the surface. It's not some magical skin that appears. It's the result of the same intermolecular forces that exist everywhere in the liquid, operating asymmetrically at the boundary. The molecules at the surface are being pulled inward by their neighbors, and that pull creates resistance to anything trying to increase the surface area. Think about what this means. If you try to push something through the surface, you're trying to increase the surface area of the water. You're trying to create more surface, more boundary between water and air. But the molecules at the surface resist this. They're being pulled inward. They don't want to spread out. They want to minimize the area, so they push back. That's what the insect is standing on. Not a physical membrane, not a solid sheet, just the collective reluctance of surface molecules to spread apart. Now here's the part that should bother you. Water molecules are moving. They're jiggling at enormous speeds. At room temperature, water molecules are bouncing around at hundreds of meters per second. They're colliding billions of times per second. The surface isn't static, it's chaos. Molecules are constantly leaving the surface, evaporating into the air. Other molecules from the air are constantly joining the surface. The boundary is a frenzy of activity. And yet, out of this chaos, the surface tension persists. How? Because what matters is the average. At any given instant, the specific molecules at the surface are different from the molecules that were there a microsecond ago. But there are always molecules at the surface. And those molecules, whoever they are at that instant, are always experiencing the same asymmetric forces. They're always being pulled inward. The tension isn't a property of specific molecules. It's a statistical property of the surface as a whole. This is a crucial insight about how the physical world works. You have chaos at the individual level. You have order at the collective level. Each molecule is jiggling randomly, unpredictably. But trillions of molecules together create patterns, create persistent properties, create surface tension that holds an insect up. Let's go back to that insect. A water strider has 6 legs. Each leg ends in tiny hairs. These hairs are covered in waxy, water-repelling substances. The insect distributes its weight across all 6 legs, and each leg makes contact with the water over a small area where the hairs touch the surface. What happens at each contact point? The insect's leg presses down on the surface. This creates a dimple, a small depression in the water. The surface bends, stretches, deforms, but it doesn't break. Why not? Because stretching the surface requires work. You have to pull those surface molecules apart, overcome their mutual attraction, increase the surface area. The surface resists, it pushes back. The water acts like an elastic membrane, deforming under the weight but not rupturing. The force that pushes back is surface tension. And as long as the force from surface tension is greater than the weight of the insect stays up. The surface deforms but holds. Now, you might wonder, why doesn't the insect just sink anyway? Couldn't it just push through with enough force? Here's the thing. The insect doesn't weigh much. A water strider might weigh about 10 milligrams. That's almost nothing. And its weight is spread across 6 legs, across many tiny contact points. The force per unit length of contact is small. The surface tension of water is strong enough to support that force. If you put something heavier on the water, or if you concentrate the weight on a smaller area, the surface will break. Drop a marble on water. It goes through instantly. The marble is too heavy, its contact area too small. The force exceeds what surface tension can support. The surface ruptures. But the insect has evolved to stay under that threshold. Light body, long legs, spread out weight, stay below the breaking point. There's another factor, the waxy coating on the insect's legs. Water doesn't wet the wax. The water molecules are more attracted to each other than they are to the wax molecules. So instead of spreading across the leg and pulling it in, the water pulls away from the leg. This creates a larger dimple, a more gradual depression, distributing the force over a wider area of surface. It's another trick to stay under the breaking threshold. Let me make something very clear. The insect is not floating. Floating is something different. When an object floats, it displaces water. It pushes water aside and sits partially submerged, held up by the buoyancy force. An object floats if it's less dense than water or if it's shaped to trap air. The water strider is not displacing water. It's not submerged at all. Its legs are resting on top of the surface on the outside of the water. The force holding it up is not buoyancy, it's surface tension. Two completely different phenomena. A boat floats because it displaces water. A water strider walks because it doesn't break the surface. These are not the same thing, even though both result in something staying above the water. Now, you might ask, why water? Why does water have such strong surface tension? Water is special. Compared to most liquids, water has unusually high surface tension. This comes from those hydrogen bonds we talked about. Water molecules attract each other strongly because of their polar nature. The positive hydrogen ends of one molecule pull on the negative oxygen ends of neighboring molecules. These attractions are stronger than the attractions between molecules in most other liquids. If you put a water strider on alcohol, it would sink. Alcohol has lower surface tension. The molecules don't attract each other as strongly. The surface is easier to break. The insect's weight would exceed what the surface could support. Water's high surface tension is part of what makes it so important for life. It allows capillary action, where water climbs up narrow tubes against gravity. It creates droplets instead of spreading into flat films. It gives water unusual behavior at surfaces and interfaces. The insect walking on water is just one dramatic demonstration of a property that matters everywhere in biology and chemistry. Let's step back and think about what we've actually learned. The insect walking on water isn't magic. It isn't some special exception to the laws of physics. It's a direct consequence of how atoms and molecules interact. At the atomic level, water molecules attract each other electromagnetically. At the surface, this attraction creates an asymmetric situation where surface molecules are pulled inward. This manifests as surface tension, a resistance to increasing the surface area. The insect, being light and distributing its weight cleverly, doesn't exceed the force threshold required to break the surface, so it stands. Every step of this explanation flows from the previous one. Atomic attraction leads to molecular forces. Molecular forces at boundaries lead to surface tension. Surface tension creates resistance. Resistance supports light objects. There's no mystery here. There's just physics, operating at scales too small to see, producing effects we observe with our eyes. But here's what I want you to notice. When someone says surface tension, they often imagine some kind of skin on the water, some thin membrane stretched across the top. But there is no skin. There is no membrane. There are just molecules, the same molecules that make up the bulk of the liquid, behaving differently at the boundary because of their position. The surface isn't a thing. The surface is a situation. It's where the liquid meets the air. And at that meeting point, the forces are unbalanced in a particular way. That imbalance creates the effect we call tension. This is important because it changes how you think about liquids. A liquid isn't a substance with a skin on top. A liquid is a collection of molecules constantly jiggling, constantly interacting with different behaviors at different locations depending on the local environment. The bulk molecules experience balanced forces. The surface molecules experience unbalanced forces. The edge molecules, where water meets the glass, experience yet another set of forces. Everything is forces. Everything is interactions. The macroscopic behavior emerges from the microscopic reality. Now consider this. The force that creates surface tension, the attraction between water molecules, is electromagnetic. The positive part of one molecule attracting the negative part of another. That's electromagnetism. The same force that holds atoms together, that makes chemistry possible, that lets you push on a table without your hand going through. When you think about it, almost every force you experience in daily life is electromagnetic. You push something, the electrons in your hand repel the electrons in the object. Electromagnetic. You stand on the floor, the electrons in your feet repel the electrons in the ground. Electromagnetic. Surface tension, electromagnetic. The insect walking on water is an electromagnetic phenomenon. The molecules are electric. Their attractions are electric. The surface tension is an electric effect, playing out at the boundary between two materials. This unifies things that seem separate. The insect on water, your hand on a table, a piece of tape sticking to a wall, a drop of water beating on a leaf. All electromagnetic interactions operating at different scales and in different configurations, producing wildly different visible effects. Let me push further. You might wonder, why don't we see surface effects everywhere? Why isn't every liquid surrounded by a visible skin? You do see surface effects everywhere. You just don't notice them because they're familiar. Watch water drip from a faucet. Why do drops form? Surface tension. The water pulls itself into spheres because a sphere minimizes the surface area for a given volume. The molecules are trying to minimize the asymmetric surface situation. They're pulling inward, pulling the water into a ball. Watch water beat up on a waxed car. Surface tension again. The water is more attracted to itself than to the wax, so it pulls into droplets instead of spreading flat. Watch a paperclip float on water if you set it down gently. Surface tension. The clip is denser than water. It should sink. But if you lower it slowly, let it rest on the surface without breaking through, the surface holds it up. These are all the same phenomenon as the insect. Surface tension, molecular, forces at boundaries. The insect is just the most dramatic, most obvious demonstration. There's something else here, something about how nature operates. The insect evolved to exploit surface tension. It didn't understand the physics. It didn't calculate the forces. Over millions of years, insects that could walk on water survived and reproduced. Their leg lengths, their body weights, their waxy coatings, all tuned by natural selection to take advantage of a physical property of water. Nature finds the loopholes. Nature exploits the physics, not through understanding but through trial and error over vast timescales. The insect is a successful experiment in surface physics conducted by evolution. And now you understand the experiment, you understand the physics behind it. You see the atoms, the molecules, the forces, the statistics. You see how chaos at the small scale produces order at the large scale. You see how the same electromagnetic force that holds matter together also creates the invisible skin that holds an insect up. This is what physics does. It takes the familiar and makes it strange, and then makes it clear. You've seen water striders your whole life. Now you see them differently. Now you see the molecules pulling each other, the surface resisting, the weight distributing, the forces balancing. The insect hasn't changed. Your understanding has. Let's think about what would happen if surface tension suddenly vanished. The insect would sink instantly. That's obvious. But think about what else would happen. Droplets wouldn't form. Water would spread into infinitely thin films. Capillary action would stop. Plants couldn't transport water up their stems. Your blood couldn't flow properly in capillaries. Soap bubbles couldn't exist. Rain would hit the ground as a mist, not drops. Surface tension shapes the world in ways you don't even notice until you imagine its absence. It's one of those background properties that enables everything else, quietly doing its job at every interface between water and air, water and glass, water and oil. The insect standing on water is a window into this hidden architecture. It's a visible demonstration of invisible forces. It's proof that the world is held together by atomic scale interactions you can't see, but can certainly observe the effects of. One more thing. I've been talking about water striders, but there are other insects that walk on water. Some beetles, some spiders, they all use the same trick. Light body, spread weight, don't break the surface. But some of them can do something even stranger. They can propel themselves. They can move across the surface, walk, run, even jump. How? By pushing against the water, not by breaking the surface, but by deforming it. They create waves, ripples, distortions in the surface. Newton's third law. Every action has an equal and opposite reaction. Push the water one way, you move the other way. The surface is elastic enough that you can push against it without breaking through. It's like skating on a trampoline. The surface gives, but it doesn't let you through. You push down and back. The surface pushes you up and forward. The insect runs across the water by creating and riding waves in the surface. This requires exquisite balance. Too hard to push and you break through. Too soft and you don't move. The insect has evolved the precise timing, the precise force, the precise leg movements to exploit the physics without violating the constraints. Every step is a physics calculation solved by evolution. Every movement is a demonstration of surface tensions, limits, and capabilities. Now you understand. The insect on the water isn't defying physics, it's demonstrating physics. It's showing you that surfaces matter, that forces at boundaries create effects you don't see in the bulk, that nature is full of phenomena that seem magical until you look at them closely enough to see the mechanics. The next time you see a water strider, watch carefully. Watch the dimples its legs create. Watch the ripples it makes as it moves. Watch how it distributes its weight, how it keeps all legs in contact, how it never puts too much force on any one point. You're watching surface tension in action. You're watching electromagnetic forces between molecules playing out at the scale of insects and ponds, producing behavior that looks like a trick but is really just physics. That's the universe. Atoms and forces all the way down, pulling, pushing, attracting, repelling, creating liquids and surfaces and tensions, allowing insects to walk on water. Not magic, not mystery, just physics doing what it always does.